the countdown has begun. Above us, beyond the soft blue veil of Earth's atmosphere, a silent monster is moving. Not the comet we've been told to watch in the news, hitting all the headlines, but another object entirely. One far closer, one far more active. One that our own telescopes did not see until the sun betrayed it. Its name is Comet C/2025 R2, the Swan, and on October 20th, 2025, it will reach its closest approach to Earth, closer than comfort should allow. Unlike 3I Atlas, which will pass our planet at a safe and distant margin, Swan has cut a path directly through the blind spot of Earth's telescopes, emerging suddenly from the sun's glare, already awake, already shedding vast clouds of gas and dust into space. We did not witness its arrival. We are witnessing its unveiling. What secrets does it carry from the distant reaches of our solar system? Is it a real threat to Earth? And why did it remain hidden until now? Join us as we explore the dangers and mysteries of a comet that emerged from the blind spot of our defenses. Let's begin. From the shimmer of solar radiation, Comet Swan revealed itself, not gradually, but in a burst of hydrogen emission that startled even seasoned astronomers. It did not appear in the night sky like a gentle whisper. It emerged like a flare in the darkness, announcing that something colossal was already here. Unlike most comets that are first detected as faint specks of reflected sunlight, Swan introduced itself through ultraviolet hydrogen emissions. These emissions were not subtle. They were unmistakable signatures of violent internal awakening. The comet had crossed its closest point to the sun just days before detection, and instead of fading quietly as it moved outward, it suddenly flared with renewed intensity. It was as if the comet had been dormant for millennia. And, at the exact moment it re-entered humanity's awareness, it chose to exhale. A comet's awakening is not peaceful. It begins when solar radiation penetrates its surface, striking ices that have been frozen since the birth of the solar system. These ices sublimate instantly, transforming from solid to gas, building pressure inside the nucleus. The surface fractures, vents erupt, and material explodes into space. Astronomers know this process well, but with Comet Swan, there was a complication. This comet was not seen before this activation. We did not witness the beginning of its transformation. We are only seeing the consequences. The Swan instrument aboard the SOHO spacecraft, designed to observe solar wind hydrogen, captured the flare. A bright, expanding cloud of hydrogen gas signaled that the comet was not just active, it was hyperactive. Hydrogen is released when sunlight breaks apart water molecules, suggesting that vast quantities of ice were being vaporized at once. This was not a steady process. It was an outburst. As the coma, the glowing atmosphere of gas and dust surrounding the nucleus, expanded, it revealed that deep materials, previously insulated beneath the surface, were now exposed. Instead of a controlled release of material, Swan was venting rapidly, indicating internal instability. This kind of behavior is often associated with comets undergoing structural stress, signs that cracks are widening, that the nucleus may be fragmenting, or that volatile reservoirs within the comet are awakening in rapid succession. And beneath all this activity lies a deeper truth. Swan is not a periodic comet we've seen before. This is a long-period comet, likely making its first return to the inner solar system since the Paleolithic age. Its ices are fresh, untouched by previous solar encounters. Its behavior is unpredictable not because it is erratic, but because it is primordial. A comet in its rawest form, reacting to sunlight not with the measured breath of a veteran traveler, but with the explosive awakening of something that has slept in darkness for tens of thousands of years. As astronomers analyzed its emissions, it became clear that this was not a passive visitor quietly drifting by. This was a body in active transformation, alive with motion, pressure, and change. It is not yet known whether the nucleus is intact or already fracturing. What is known is that Comet Swan is now fully awake, and its journey is only beginning. while the world was fixated on 3I Atlas, comfortably distant and interstellar. Comet Swan crept through the solar glare, unseen. It is not the visitor from another star that we were told to watch. It is the one born in our own cosmic backyard, moving much closer than any headline dared to warn. 3I Atlas captured the world's imagination. Its interstellar origin made it a scientific curiosity, a cosmic outsider passing harmlessly through our solar system. Astronomers reassured us that it posed no risk and that it would travel at a safe distance, gliding through the outer realms and then vanishing forever into the void. The media spotlight followed it closely, fascinated by the idea of a messenger from another star system. But while telescopes were pointed outward, searching the far reaches of space for exotic intruders, another object approached from a far more perilous trajectory. Comet Swan did not arrive from the galactic unknown. It emerged from our own Oort cloud, a reservoir of icy debris encircling our solar system. This is not a foreign visitor. This is a native, shaped by the same gravitational forces that govern Earth. And unlike 3I Atlas, Swan's path does not carry it far beyond the orbits of the inner planets. It cuts across the plane of the solar system itself, threading a course dangerously intertwined with Earth's orbital region. What makes this even more striking is how Comet Swan was discovered. It did not appear gradually in the outer solar system, as most long-period comets do. It appeared suddenly, already active, already venting gas, already near the Sun, meaning it had passed through the one part of the sky we are least equipped to observe: the solar blind spot. While our attention was drawn to 3I Atlas, a known trackable object safely distant, Comet Swan was emerging from solar brightness, invisible to optical telescopes, detectable only through ultraviolet hydrogen emissions. This was not just a matter of oversight, it was an illustration of vulnerability. We are adept at tracking distant, steady objects with predictable behavior. But Swan was neither distant nor steady. It had already experienced the most volatile part of its journey, its solar encounter, before we even saw it. And that encounter changed it, activating it, perhaps destabilizing it. We are now observing the comet not at the start of its transformation, but after it has already begun reacting violently to the Sun. This is why Swan is not simply another comet. It is the unexpected variable, the one that reminds us how much can still evade our systems. While 3I Atlas moves past us as a piece of interstellar trivia, Comet Swan demands our focus. It is active, volatile, and approaching far closer. It is shedding material into a space we will soon occupy. It has already defied our expectations once, by existing in the first place, undetected until after perihelion. And so the question becomes not whether Swan is like 3I Atlas, but whether it is the comet we should have been watching all along. Swan was not uncovered by sweeping telescopes, but by accident, spotted in ultraviolet data meant to study the solar wind. It was never supposed to be seen then. Yet it appeared, as if the universe itself had decided to reveal a secret at the last possible moment. Astronomers spend years designing surveys to search for comets and asteroids that could pose a risk to Earth. They map the sky methodically, scanning regions opposite the Sun, where shadows and darkness reveal what light normally conceals. They build dedicated telescopes designed to find faint moving objects. But Comet Swan slipped past all of them. It was not detected through these deliberate efforts. Instead, it emerged indirectly, revealed through hydrogen emissions captured by the SWAN, solar wind anisotropies, instrument aboard the SOHO spacecraft, which was not even looking for comets. The SWAN instrument was built to monitor solar wind, streams of charged particles from the Sun, and track hydrogen absorption across interplanetary space. In these ultraviolet observations, astronomers suddenly noticed an anomaly: a bright, expanding cloud of hydrogen that did not match any known solar activity. It was not part of a coronal mass ejection. It was not from the Sun itself. It was coming from a single point, moving rapidly, a comet. What stunned scientists was not just the comet's presence, but its timing. By the time it was detected, Comet Swan had already passed perihelion. It had already experienced its closest approach to the Sun, already undergone its most intense heating phase. Most comets are discovered months before this moment, allowing astronomers to observe their activation gradually. But Swan was discovered after this phase, meaning we missed the beginning of its awakening, the moment when its internal chemistry came alive. This has left astronomers working backward. Instead of studying the cause, they are studying the effect. Instead of observing the comet's initial outgassing, they are seeing only the aftermath. Like walking into a room after an explosion and trying to determine what triggered it. And this leads to deeper questions. How large was the outburst that first activated Swan? Did it fragment while still hidden in the solar glare? Did its orbit shift as material erupted from its surface? We do not know. We may never know. This discovery was not supposed to happen this way. In an era when we pride ourselves on constant surveillance of near-Earth space, the appearance of a large, active comet after its most critical moment is a reminder that there are still blind spots, places in the sky where enormous objects can reside unseen. Comet Swan did not raise its hand and announce its arrival. It appeared fully awakened, already transformed, as if emerging from behind a curtain drawn across the sun. And in doing so, it posed a silent, unsettling question. If this comet was already here, what else might be waiting behind the glare, still unseen? Long before human civilization took its first breath, this comet began its descent. Each particle of ice within it holds the memory of a time before planets had names, preserved relics from the solar system's birth. Comet Swan did not form in the age of humans, nor in the age of dinosaurs. It predates mountains, oceans, and continents. It is a direct remnant from the primordial nebula, the swirling cloud of gas and dust that collapsed under gravity 4.6 billion years ago to form our Sun and all the planets. While Earth evolved, erupted, and transformed over eons, this comet remained unchanged, residing in the outermost reaches of the solar system, where time itself seemed to slow. There, in the remote Oort cloud, sunlight is a distant whisper, not a force. Temperatures hover near absolute zero. There are no seasons, no storms, no collisions, only stillness. It is in this quiet cradle of deep space that objects like Comet Swan have waited since the beginning. Locked in cold storage, untouched and perfectly preserved. When Swan began its inward journey, it was not the start of a new story, but the continuation of an ancient one finally returning to light. This is what makes long-period comets so scientifically sacred. They are time capsules. Unlike planets that have been reworked by geology and erosion, comets preserve material exactly as it was in the solar system's infancy. Every grain of dust, every molecule of ice within Swan's nucleus is a message from a time before Earth existed. As Swan approached the Sun, the first layers of this ancient ice began to sublimate. In that moment, 4.6 billion years of cosmic history were released into space as vapor. Instruments detecting hydrogen and carbon compounds from the comet's coma were not studying something new. They were studying the beginning of everything we know. Within those emissions may be the same types of molecules that once fell to Earth in comets billions of years ago, possibly delivering the water in our oceans and the organic compounds that led to life. There is a profound irony here. While Swan is awakening now, its story has already been written across epochs of time. The comet is not just moving through our solar system. It is returning to its birthplace, reenacting a journey it may have taken once before, in an era when Earth was nothing more than molten rock beneath a toxic atmosphere. For humanity to witness this is extraordinary. We are watching a celestial memory awaken, not a memory in our minds, but in the very molecules that once formed our world. As Swan continues its inward passage, shedding the layers that time forgot, it invites us to do the same, to look backward, to remember where we came from, and to realize that this is not just a comet passing Earth. It is a piece of our own origin story, coming home. Comet Swan did not raise its hand and announce its arrival. It appeared fully awakened, already transformed, as if emerging from behind a curtain drawn across the sun. And in doing so, it posed a silent, unsettling question. If this comet was already here, what else might be waiting behind the glare, still unseen? There is a region of the sky where Earth's instruments cannot look, where the sun's light blinds even our greatest observatories. Comet Swan passed directly through this region, hiding in plain sight, as though the cosmos had carefully placed a curtain across our view. Every night, as darkness falls, observatories across the globe open their domes and begin scanning the heavens. They track galaxies billions of light years away, catalogue exoplanets orbiting distant stars, and measure the slow motions of near-Earth asteroids. But despite this reach, there is a place our telescopes dare not look, a forbidden zone just a few degrees from the sun. Not because we don't want to, but because we cannot. The overwhelming glare of our star washes out everything near it, turning even the largest comet into an invisible phantom. This is known as the solar blind spot, a cone of invisibility surrounding the sun that stretches across our field of view. It is a fundamental vulnerability, created not by negligence, but by physics itself. Earth's atmosphere scatters sunlight, making the region near the sun impossibly bright. Telescopes that attempt to peer into this glare risk damage to their sensors, like human eyes staring directly at noonday light. So, we avert our gaze. And in that space, hidden in brilliance rather than shadow, comets like Swan slip unnoticed into the inner solar system. This blind spot is not static. It shifts with Earth's rotation, tilting with the changing seasons. Objects that move through it can remain undetected for days, weeks, or months, depending on their speed. Swan navigated this zone with perfect timing, passing perihelion, its closest approach to the sun, while still cloaked in solar glare. By the time it emerged, it was already active, already brightening, already on its outbound journey toward Earth's orbital path. For planetary defense experts, this is the worst-case scenario, not an impact, but a surprise. A comet does not need to collide with Earth to pose risk. It can fragment, shedding debris that intersects Earth's orbit. It can release meteoroid streams that threaten satellites and spacecraft. But we cannot prepare for what we cannot see. Ground-based telescopes are not our only eyes in space. Instruments like SOHO, Stereo, and Parker Solar Probe monitor the sun constantly. Yet even they are not designed to detect comets with precision. Their focus is on solar wind dynamics, coronal mass ejections, and magnetic fields, not icy wanderers from the edge of the solar system. Comet Swan was only visible in ultraviolet images designed to detect hydrogen, the byproduct of sublimating water ice, which happened purely by chance. This raises a profound question. If a comet of this size can slip through undetected until it is already inbound, how many others have passed through this same hidden gate, unseen? The blind spot is not an oversight. It is a vulnerability etched into the limits of our technology. We have mapped the galaxies. We have photographed black holes. But just a few million miles from our home star, there is still a place where darkness thrives in light. And in that brightness, Comet Swan arrived, silent, unseen, unstoppable, until the sun itself, in illuminating it, betrayed its presence. Unlike most comets first seen through reflection, Swan betrayed itself through hydrogen gas fluorescing in ultraviolet light. It was not reflecting the sun's rays, it was reacting to them, expanding rapidly, alive with unexpected activity. When a comet awakens, its first response is chemical. Sunlight does not simply illuminate it, it transforms it. As Comet Swan approached the sun, radiation began striking its surface, triggering the sublimation of water ice buried deep within its nucleus. Each molecule of water, once released, was broken apart by solar ultraviolet radiation into hydrogen and oxygen atoms. The hydrogen, now free, scattered into space and began to fluoresce in a specific ultraviolet wavelength known as Lyman alpha, a signature unmistakable to instruments tuned to detect it. The surge was explosive. Hydrogen emissions from SWAN were not mild or gradual. They intensified rapidly, indicating that vast reserves of water ice were suddenly exposed and vaporizing at extraordinary rates. This was not the behavior of a stable surface warming slowly. It was the sign of a volatile body in upheaval, cracking, venting, and perhaps undergoing internal stress that extended deep beneath its crust. Ultraviolet detectors, unlike optical telescopes, do not rely on reflected light. They see the energetic fingerprints of chemical reactions that reveal the comet's true activity. What those detectors saw in SWAN was a hydrogen envelope expanding millions of kilometers outward, forming a ghost-like sphere far larger than its visible coma. In ultraviolet, Comet SWAN was not a dim wanderer. It was a beacon. This hydrogen surge reveals critical information. It tells us SWAN is rich in water, one of the primary components of primordial comets. It suggests that its ices have remained pristine, unexposed to the sun for tens of thousands of years, until now. And most importantly, it signals that the comet is undergoing active change, possibly from internal sources of pressure, not merely from sunlight striking its surface. Some comets release hydrogen steadily. Others release it erratically, in bursts. SWAN belongs to the latter category. Its hydrogen signal fluctuated, rising sharply and then stabilizing, then rising again, indicating multiple outgassing events. These could be caused by rotational effects, with different regions of the nucleus being exposed to sunlight at different times, or by internal fracturing as pressure builds beneath the surface. Each surge changes the comet's trajectory ever so slightly. Hydrogen gas escaping from one side acts like a microscopic rocket engine, imparting thrust. Over time, this non-gravitational acceleration can alter the comet's orbit, changing its approach distance, its speed, and its future return path. In other words, the hydrogen we observe is not just a signal of chemical activity, it is a sign of motion. The surge in ultraviolet light was how we first saw Comet SWAN. It was the comet's own exhalation that revealed its presence. It announced itself not through reflection, but through reaction, a body awakening so rapidly that the space around it glowed. And as hydrogen flooded into the void, astronomers realized, this comet is not merely passing by. It is changing, and it is accelerating. It is not coming directly for Earth, but the path it traces through space cuts alarmingly close to our orbit. In cosmic terms, this is a near touch, and in the open stillness of space, proximity is everything. Comet SWAN's journey is governed by celestial mechanics. Ancient, predictable, mathematical. Yet what makes its trajectory so compelling is not where the comet is now, but where its orbit intersects with ours. Astronomers use a critical metric called the minimum orbit intersection distance, or MOID. For Comet SWAN, that value has been calculated to be just 0.048 astronomical units, about 7 million kilometers. This is not the distance SWAN will pass by Earth during this approach, but the distance between the paths of Earth and the comet. That distinction is crucial. Think of Earth and SWAN as two runners on separate lanes of a circular track. They are not colliding, but their lanes nearly overlap. If one runner stumbles, or if the track shifts even slightly, the gap between them can close. In the cosmos, gravitational influences, solar radiation, and outgassing can act like those small shifts, altering trajectories over time. While SWAN's predicted closest approach during this passage is around 39 million kilometers, comfortable by planetary standards, the MOID indicates that the comet's orbital path is braided closely with Earth's own. This orbital alignment carries long-term implications. Even if the nucleus of Comet SWAN never approaches Earth directly, the debris it sheds, dust, fragments, icy particles, remain scattered along its orbital path. As Earth continues its annual journey around the Sun, It may one day intersect this trail, passing through regions of space where fragments of the comet linger invisibly in the dark. Moreover, the comet's shallow inclination, relative to the plane of the solar system, makes its path unusually significant. Many long-period comets dive in from steep angles, crossing Earth's orbital zone quickly and then departing. Swan, however, travels on a trajectory that aligns more closely with Earth's orbital plane. It is not merely a passerby, it is a traveler moving almost parallel to our path, increasing the potential for long-term interaction between Earth and its debris. And there is another subtle but vital factor: outgassing. As Swan releases jets of gas, these act as thrusters, shifting its orbit slightly. Even a change measured in millimeters per second can, over millions of kilometers, alter its approach distance dramatically. This makes long-term predictions inherently uncertain. The path we calculate today is not the path that will remain forever. The geometry of Swan's orbit is not a cause for alarm, but it is a cause for attention. It is a reminder of how closely Earth's fate is intertwined with celestial bodies we cannot control. The cosmos is not a static backdrop. It is dynamic, alive with motion, governed by invisible forces acting across vast stretches of time. With Comet Swan, we are witnessing such a moment of motion, an approach not defined by collision, but by proximity, a cosmic near touch that echoes with possibility. And as the comet continues along its path, the question is no longer if it will influence Earth, but when and how its presence will be felt. In late September, the comet brightened suddenly, as though something inside it had ruptured. Such outbursts are not merely visual, they are signs of internal pressure, instability, and the possibility that pieces may break away. Comets are not solid, unchanging bodies. They are fragile composites of ice, dust, and rock, held together by gravity so weak it could be overcome by the pressure of a human hand. When sunlight penetrates their surface, it awakens volatile materials within, creating internal forces that can reshape their entire structure. For Comet Swan, this awakening manifested not as a gradual increase in brightness, but as an explosive surge, one that caught astronomers off guard. Telescopes monitoring the comet recorded an abrupt jump in magnitude, far beyond what standard models predicted for that stage of its orbit. Its coma expanded rapidly, shedding vast amounts of gas and dust in a short span of time. This was not simply a response to solar heating, it was indicative of something deeper, a sudden exposure of new material, likely caused by internal fracturing or rotational stress, tearing open fresh vents on the surface. Cometary outbursts can be caused by several mechanisms. The most common is thermal fracturing, where the intense heat from the sun causes the surface to crack. When this occurs, dormant layers of ice are exposed, releasing trapped gases in powerful jets. Another possibility is cryovolcanic activity, where subsurface pressure builds until it erupts violently, similar to a geyser on Earth. And in the most dramatic cases, outbursts can signal partial fragmentation, where a piece of the comet's nucleus breaks away entirely. Astronomers began analyzing the light curve and structure of Swan's coma, searching for signs of multiple condensation points, evidence that fragments may already be separating from the main body. Early data suggested irregularities, subtle yet significant, pointing to uneven outgassing. This means that Swan's nucleus may no longer be a single, stable object. It may be evolving, transforming in real time. More concerning is the timing of this outburst. It occurred after perihelion, when the comet was expected to begin fading. Instead, it intensified. Such delayed activity is often a hallmark of internal heat redistribution. As the outer layers cool, deeper layers, still warming from solar radiation absorbed earlier, begin to activate. It is a delayed ignition, an aftershock following the main event. If Comet Swan has indeed begun to fracture, this is a turning point not only in its journey, but in its legacy. Fragmentation increases the potential for debris streams Earth could one day intersect. Even if the nucleus remains intact during this passage, The fragments released during outbursts may follow slightly altered trajectories, spreading along the comet's orbit like pearls slipping from a broken strand. This mysterious outburst is not merely a moment of beauty, a signal that the comet is changing, that its internal forces are awakening, that its future path, and the path of whatever pieces it leaves behind, may diverge from what we once predicted. Comet Swan is speaking, not in words but in light, and the message is clear. Something within it has broken free. Despite the brightness of its coma, the core of Comet Swan remains invisible. Hidden within the glowing veil, its solid body could be a few kilometers across, or far larger. The truth is still cloaked in the unknown. What we see when we observe a comet is not the comet itself, but its reaction to sunlight. The coma, the vast halo of gas and dust, can extend millions of kilometers into space, dwarfing the solid object at its center. This makes comets deceptively difficult to measure. A small nucleus with high activity can produce a large coma, while a massive nucleus with low activity may appear faint. In the case of Comet Swan, its sudden surge in brightness has led to competing theories about its true size, and each carries different implications for its behavior, stability, and future. Direct imaging of the nucleus is nearly impossible from Earth due to the brightness of the surrounding coma. Instead, astronomers must rely on indirect measurements. The rate of outgassing, the comet's brightness curve, and the velocity of material escaping from the surface. But all of these are influenced not only by the size of the nucleus, but by its composition and level of activity. If Swan is a small comet, perhaps only 1 to 3 kilometers wide, it would need to be extraordinarily active to produce the observed hydrogen emissions. This level of activity could indicate that the comet's internal structure is unstable, with large portions of its surface actively sublimating at once. Small comets are far more susceptible to fragmentation, as they lack the gravitational strength to hold themselves together if internal pressures rise. If Swan is a large comet, potentially 10 kilometers or more in diameter, it may still have vast reservoirs of untouched ice within its core. Such a nucleus could sustain powerful outbursts without immediate danger of disintegration. Larger comets are capable of surviving multiple perihelion passages, sometimes growing more active over time as their surfaces fracture and expose fresh ice. Then, there is a more complex possibility. Swan may not be a single nucleus. Its fluctuating brightness and irregular hydrogen emissions could indicate multiple active regions or multiple fragments moving as a loosely bound cluster. In historical cases, such as Comet Biela in the 1800s, a seemingly stable comet suddenly split into 2 pieces, each developing its own coma and tail. A split nucleus would explain Swan's uneven brightness profile, and it would increase the likelihood of debris remaining in its wake. This uncertainty matters. A large, intact nucleus suggests long-term stability, but also the potential for a larger debris field trailing behind it. A small, unstable nucleus suggests imminent fragmentation, creating multiple new bodies that could shift onto different orbital paths. And a fragmented nucleus indicates a complex future, with each piece following slightly different gravitational influences. Right now, Comet Swan is a question without an answer. We can measure its light, its speed, its tail, but not its heart. And until we know the size of its nucleus, we cannot know the scale of its potential legacy. It is not the light we see that defines Swan, it is the hidden mass within that light, holding secrets we have only just begun to uncover. Comet Swan does not trail a single tail, but multiple threads of ionized particles and rocky dust stretching millions of kilometers into space, like cosmic ribbons unraveling behind a fleeing giant. A comet's tail is not merely a visual display, it is the comet's biography written across the sky. Each tail tells a different story about its internal composition, its interaction with the solar wind, and the forces acting upon it. In the case of Comet Swan, 2 distinct tails have formed, one made of dust, heavy and ancient, and the other composed of charged ions, light and ethereal, sculpted by invisible solar forces. The dust tail is formed from particles lifted off the comet's surface as ice sublimates. These grains, some as fine as smoke, others the size of pebbles, are pushed away from the nucleus by the pressure of sunlight. Unlike light, dust carries momentum, so it moves slowly, tracing the comet's curved orbital path. This results in a sweeping arc that lingers long after the comet has passed, leaving behind a persistent trail that may one day intersect Earth's orbit. This tail is composed of material older than Earth itself, remnants from the primordial nebula out of which all planets formed. Each dust grain carries within it clues about the origin of the solar system: minerals, carbon compounds, and possibly even organic molecules that may once have formed the seeds of life. The ion tail tells a different story. As the comet releases gases, primarily water vapor, carbon monoxide, and carbon dioxide, these molecules are broken apart by ultraviolet radiation from the sun. The resulting ions are captured by the solar wind, a stream of charged particles emanating from the sun at over 1 million kilometers per hour. These ions are then funneled along the lines of the solar magnetic field, forming a tail that stretches directly away from the sun, sometimes spanning tens of millions of kilometers. Unlike the dust tail, which curves, the ion tail forms a straight, almost rigid beam of charged particles. It glows in vivid blues and greens as ionized carbon and cyanogen fluoresce under solar radiation. These tails can exhibit kinks and disconnections when struck by solar storms, clear signs that the comet is not traveling through empty space, but through a dynamic environment shaped by the sun's ever-changing outflow. This dual-tail structure is not merely beautiful, it is a diagnostic tool. By studying the angle, brightness, and composition of each tail, astronomers can determine how intensely the comet is reacting to solar radiation, how rapidly it is losing mass, and whether it is undergoing internal instability. In Comet Swan, the ion tail's fluctuations suggest bursts of activity, possibly caused by rotational exposure of new ice regions or even fragmentation events. More intriguingly, these tails do not disappear when the comet does. As Swan continues along its orbital path, the dust it leaves behind forms a debris field that Earth may cross in the future. Over years or centuries, gravitational interactions with planets can shift this debris into Earth's orbital lane, where it may manifest as meteor showers or, in extreme cases, meteor storms. The tails of Comet Swan are not mere byproducts of its journey. They are the comet's legacy, and long after Swan has vanished back into the darkness, its tails may continue to write their story across Earth's sky. Comets are fragile. They do not merely travel, they fracture. And when they do, their fragments spread along their orbit like shrapnel, each piece a potential hazard on a path that crosses Earth's own. Unlike asteroids, which are often solid rock or metallic cores, comets are loosely bound collections of ice, dust, and primordial material, cosmic snowballs held together by the weakest of gravity. They were not built to last. They were not shaped for survival. They are remnants from the dawn of the solar system, frozen in time, unchanged because nothing has yet forced them to change. Until now, when a comet like Swan nears the sun, it is thrust into a world of radiation, tidal forces, and thermal stress. This is where comets awaken, and where many of them meet their end. Fragmentation is not an anomaly, it is a natural phase in a comet's life cycle. Just as tectonic plates shift on Earth, a comet's crust can crack under internal stress. Sometimes the cracks are small, a vent forms, releasing gas in a focused jet, but sometimes the pressure is too great. The comet splits apart, revealing fresh ice beneath, which sublimates rapidly, creating a sudden burst of brightness. What appears from Earth as a beautiful flare-up is, in truth, a catastrophic failure of the comet's structural integrity. We have witnessed this before. In 1994, Comet Shoemaker-Levy 9 fragmented into more than 20 pieces after passing too close to Jupiter. Those fragments, bound no longer to each other but each to their own trajectory, slammed into the giant planet one after another over the course of a week. The explosions were so massive they could be seen from Earth. In 2006, Comet 73P Schwarzmann-Wachmann disintegrated spectacularly, its pieces stretching across millions of kilometers. Even Halley's Comet, one of the most famous in human history, is slowly breaking apart, leaving behind a trail of debris responsible for multiple annual meteor showers we still witness on Earth. Comets break. It is what they do. And now, we look to Comet Swan. Its sudden outburst suggests internal instability. The brightness fluctuations indicate the coma may not be emanating from a single point source. If Swan is fracturing, it is not merely shedding dust. It could be releasing large chunks of itself into space. These chunks can follow similar orbits, but slight differences in their velocities cause them to spread over time, forming a debris trail that Earth may later encounter. Even a fragment as small as 100 meters wide could, if it entered Earth's atmosphere, release the energy of a nuclear explosion through airburst. If larger pieces exist, kilometer-sized fragments, they would be capable of causing regional or even global effects. Such an event is still extraordinarily unlikely during this passage, but the geometry of Swan's orbit ensures that all debris it leaves behind remains permanently intertwined with Earth's trajectory. The fragility of a comet is not only a scientific curiosity, it is a reminder of the dynamic, evolving nature of our solar system. These are not static objects. They are active, living relics. And when they break, they leave breadcrumbs across the sky, breadcrumbs that planets like ours may one day cross. Comet Swan is not just passing by, it is changing as it travels, and each change writes a new chapter in a story that leads, ultimately, toward our world. Astronomers measure danger not just by impact, but by intersection. And Comet Swan's minimum orbit intersection distance, 7 million kilometers, is smaller than the safe margin most comets ever breach. This value, known as the moid, is not a prediction of an impact. Rather, it is the closest that two orbital paths can approach one another in three-dimensional space. Imagine two invisible highways wrapping around the Sun, each carrying a celestial traveler. If those highways pass within a few million kilometers of each other, it means that over long timescales, with subtle shifts and outgassing, there is a mathematical possibility, in some future cycle, that the travelers might occupy the same point in space at the same time. For perspective, most long-period comets never come within tens or even hundreds of millions of kilometers of Earth's orbital path. A moid of less than 0.05 astronomical units, as is the case with Comet Swan, immediately places it into a category astronomers classify as potentially hazardous, not because it is currently on a collision course, but because its orbital geometry is intertwined with our planet's own. And this is where the story becomes particularly compelling. At its closest approach during this pass, Comet Swan is expected to remain about 0.26 astronomical units away from Earth, around 39 million kilometers. That seems vast by human standards. But comets are not static bodies. Their orbits are influenced not only by gravity, but by their own activity. Every time the Sun heats the surface, gas erupts outward, acting like a thruster. These non-gravitational forces can alter the path by tiny amounts, changes so small they are measured in millimeters per second. Yet compounded over time, those subtle shifts can amount to tens of thousands of kilometers. Now consider fragmentation. If the comet splits into pieces, each fragment will experience outgassing independently. Their trajectories will diverge. The main nucleus may follow the predicted path, but the fragments could drift inward or outward, changing their moid relative to Earth. Once a comet has a moid this small, every fragment becomes a new question, a new possibility. It is important to emphasize, no one is suggesting an imminent collision from the main body of Comet Swan during this passage. But the 7 million kilometer threshold places it in a realm where probability, not certainty, rules the narrative. It ensures that Comet Swan, and any material it sheds, will remain dynamically relevant to Earth's orbital environment for years, perhaps centuries to come. Because the MOID is not static, it evolves. Even after the comet retreats into the depths of the solar system, The trail it leaves behind, dust, ice, rock, remains strewn along its orbit like cosmic pollen. Earth, orbiting the Sun on a predictable schedule, may intersect with that material again and again. If the MOID decreases over time due to orbital perturbations or gravitational nudges from planets, future generations may witness meteoric storms or even atmospheric entries caused by fragments that were part of this very comet. This threshold, then, is not merely a number. It is a whisper from the mechanics of the universe itself, a gentle reminder that space is not empty and that our planet moves through a cosmic web of possibilities. 7 million kilometers. In the language of orbital mathematics, it says, "We are close enough to matter." As Swan vents its ancient ices, the pressure of escaping gas acts like a rocket engine, changing its trajectory slightly. A slight change in space can become a vast shift over millions of kilometers. We often imagine celestial bodies as fixed in their orbits, following predetermined paths laid out by gravity alone. But comets are not passive travelers. They are engines, alive with energy, constantly reshaping their own journey. As sunlight strikes the comet's surface, pockets of ice suddenly sublimate, transforming from solid to vapor in an instant. This vapor escapes in jets that erupt from the surface, pushing against the nucleus, just as exhaust propels a rocket. It is not loud. It is not dramatic. It is subtle, gentle, unceasing, and in the realm of orbital mechanics, subtlety is everything. This process is called outgassing, and it is the heartbeat of every active comet. With each burst of gas, the comet accelerates or decelerates by a tiny fraction. To the human mind, the effect seems negligible. But in the language of space, where distances are measured in millions of kilometers and orbits take decades or centuries to complete, even a change of a single millimeter per second can send a comet hundreds of thousands of kilometers off its expected path. Comet Swan is already exhibiting signs of non-gravitational acceleration. As its hydrogen emissions increased, scientists noticed minute deviations between its observed position and the one predicted by pure gravitational models. These deviations are not errors. They are signatures, evidence that powerful internal forces are at play. What makes this especially important is Swan's current orbital geometry. Its path crosses near Earth's orbital plane. When a comet is on such a trajectory, even slight alterations can shift the distance of closest approach. If outgassing occurs more strongly on one side of the nucleus than the other, the resulting thrust can tilt or stretch the orbit. While these changes are not expected to bring the main nucleus into collision with Earth, they can affect the dispersion of dust and potential fragments, the parts of the comet we cannot yet see. Think of a spinning garden sprinkler. As water is ejected through one nozzle, the sprinkler rotates, shifting its aim. Similarly, as Swan rotates in space, each jet of outgassing can apply thrust in a different direction, depending on the comet's orientation. This creates a constantly evolving force field around the nucleus, influencing both its rotation and trajectory. If outgassing is symmetrical, the net effect is small. But comets are rarely symmetrical. Their surfaces are uneven, their vents irregular, their interiors chaotic. In fact, astronomers believe that the recent brightening events, sudden bursts of ultraviolet activity, are directly linked to rotational exposure. As Swan spins, dormant regions of ice are temporarily exposed to the sun, triggering rapid sublimation. It is as though the comet breathes in shadow and exhales in sunlight. The long-term result is an unpredictable path. Over the vast arc of its orbit, these microforces may alter the comet's return period by years or even decades. If fragments have already separated, each one will feel these forces differently, spreading them along the orbit like beads on an invisible thread. Outgassing is not a side effect. It is the engine of fate for a comet, and in the case of Comet Swan, it is the reason astronomers are watching not just where it is, but where it might be driven next. The comet's coma widened unexpectedly, not fading with distance as typical comets do, but expanding, as if something deeper was awakening within it. A coma is more than a cloud of mist trailing a comet. It is the very breath of the comet itself, a visible aura created as sunlight strikes ancient ices, transforming them into gas and dust. Typically, as a comet moves away from the Sun after perihelion, its coma begins to shrink. The solar energy decreases, the sublimation slows, and the comet gradually returns to dormancy. But Comet Swan broke that pattern. In the days following its closest approach to the Sun, when its activity should have begun to subside, the coma instead began to grow. Observatories tracking its ultraviolet emissions noted a steady increase in hydrogen and carbon-based gases. The dimensions of the coma swelled, stretching millions of kilometers outward. It was not merely persisting in activity, it was intensifying. Why? The answer may lie beneath the comet's surface. As Swan heated during its encounter with the Sun, it likely developed fractures that extended deep into its interior. These cracks can act as conduits, exposing fresh pockets of ice that were previously insulated from heat. Unlike surface ice, which vaporizes quickly and leaves behind dust, these subsurface reservoirs can release volatile gases in powerful bursts, long after the comet has moved into cooler regions of space. In essence, Comet Swan is revealing its layers one by one. Every moment it travels through the inner solar system, new material awakens, molecules that have been frozen since the birth of our star. And as those molecules vaporize, they are not just expanding the coma, they are launching gas jets that shape the comet's rotation, alter its trajectory, and potentially destabilize its structure. Astronomers are now observing fluctuations in the coma's brightness, subtle oscillations that may indicate rotational exposure. As the comet spins, new vents are exposed to sunlight, generating localized bursts of activity. These bursts are not uniform. They are sporadic, irregular, and unpredictable, suggesting that the comet's surface is a patchwork of dormant regions and hyperactive zones. At the same time, the coma's chemical fingerprint is changing. Spectroscopic analysis shows increasing levels of carbon compounds and neutral hydrogen, signs that deeper, more volatile, rich material is being reached. This is not surface frost evaporating, it is the core beginning to speak. And with that awakening comes uncertainty. A growing coma may seem harmless, even beautiful, but it raises several deeply important questions. Is the comet's nucleus intact? Or is it fragmenting internally? Are new vents forming due to rotational stress? Could the increasing outgassing indicate imminent structural breakup? And, most critically, what will happen when this expanding coma interacts with the gravitational pull of Earth's orbital region? Comets are not permanent objects. They are ephemeral, changing entities. Every second, Comet Swan is shedding mass that does not disappear but remains behind along its orbital pathway. As the coma grows, so too does the volume of potential debris. Every molecule of ice, every grain of dust, every fragment of rock released into that expanding cloud becomes part of a trail. A trail Earth may cross. What began as a simple glowing halo has become something more. A sign that Comet Swan is not quieting down, it is rising in power, revealing not just its presence, but its potential. And with every kilometer it travels, the questions continue to multiply. Comet Swan is likely a messenger from the Oort cloud, the frozen halo at the edge of our solar system. Objects from this realm return only once every tens of thousands of years, if ever. To imagine the Oort cloud is to imagine the solar system breathing. Far beyond the orbit of Neptune, past the Kuiper belt and the scattered disk, farther still than Pluto's lonely path, lies an almost unimaginable realm, a vast spherical shell composed of icy bodies, trillions in number, surrounding the Sun like a ghostly cocoon. These are the leftovers of creation, primordial fragments cast outward during the birth of the planets, held in place by the faintest tug of the Sun's distant gravity. This is the Oort cloud, a place we have never seen directly, but whose existence is inferred by the visitors that emerge from its depths. Comet Swan is one of these visitors. It did not form near the planets. It was not shaped by collisions or by the warmth of the sun. It has spent nearly its entire lifetime in darkness, untouched, unchanged, suspended in a cosmic sleep lasting tens of thousands, even hundreds of thousands of years. Only a gravitational nudge, perhaps from a passing star or the tidal influence of the Milky Way itself, could have dislodged it, setting it on a slow, spiraling inward journey. Unlike short-period comets that return every few years or decades, long-period comets like Swan follow elongate orbits spanning millions of years. When they fall toward the Sun, they accelerate rapidly, gaining speed and shedding ice as they warm. Their moment in the light is brief, their return to darkness nearly eternal. And this is what makes Swan extraordinary. We are witnessing not just the comet itself, but a moment in cosmic history, a once-in-an-epoch event. The last time Comet Swan visited the inner solar system, humanity was in the late Paleolithic era. Glaciers sculpted the continents. Mammoths roamed the tundra. Our species may have watched this same comet glimmer in the sky, not knowing that it would be tens of thousands of years before it returned. Oort cloud comets carry with them the unaltered chemical fingerprints of the early solar system. Unlike planets, which have been shaped by volcanism, erosion, tectonics, and atmosphere, comets preserve the earliest material in its original state. That means Swan is not just a visitor, it is a time capsule. Inside its icy core are molecules unchanged since the solar nebula first collapsed to form the Sun and planets. Scientists have detected water vapor in such comets chemically similar to Earth's oceans, supporting the theory that long-period comets may have delivered water to Earth billions of years ago. Organic molecules, precursors to life, have also been discovered in cometary material. So, as Comet Swan draws near, we are not merely observing a celestial object, we are encountering our own origins. To watch this comet is to look backward in time, to see, not with our eyes, but with our understanding, the story of how Earth became a world of oceans and sky. The Oort cloud is not just the edge of our solar system, it is the cradle of our past, and perhaps the key to our future. And from that cradle, Comet Swan has awakened, carrying in its icy heart a message billions of years old, now finally returning to the light. Scientists are already drawing parallels to comets that have fragmented in Earth's vicinity, including the one that likely caused a global event over 13,000 years ago. Swan's behavior echoes some of these ancestral visitors. Throughout history, great comets have not merely been astronomical events, they have been turning points. They have been recorded in ancient chronicles, painted on temple walls, and etched into the memories of civilizations long vanished. These celestial wanderers arrived unannounced, shimmering across the skies like omens, often preceding times of upheaval, change, or mystery. Today, in our era of satellites and equations, we no longer fear comets as harbingers of doom, but we still study them closely because the past has shown us that comets are not always passive visitors. Some have fractured, some have exploded, some have left behind trails of debris that rained upon Earth. Comet Swan is beginning to exhibit the same signatures. One of the most studied historical events tied to a comet is the Younger Dryas impact hypothesis. Around 12,800 years ago, the Earth experienced a sudden and dramatic cooling event, coinciding with continent-spanning wildfires and the extinction of megafauna across North America. Ancient glass-like material, known as impact spherules, and layers enriched with platinum, common in cosmic objects, suggest that a fragmented comet or swarm of cometary debris may have impacted Earth's atmosphere. Scientists theorize this material originated from a long-period comet that had begun to disintegrate, sending fragments across Earth's orbit. Swan, too, is a long-period comet exhibiting unexplained outbursts and signs of internal stress. Then there is Comet Shoemaker-Levy 9, which shattered into more than 20 pieces after passing too close to Jupiter in 1992. The fragments plunged into the gas giant 2 years later, each impact releasing energy equivalent to millions of nuclear bombs. Though this comet never threatened Earth directly, it provided a sobering demonstration of what can happen when a comet succumbs to tidal forces and splits apart. Comet Swan's increasing activity, growing coma, and fluctuating brightness could be early signs of similar fracturing, this time potentially in Earth's own orbital neighborhood. We also look to Comet 73P, Schwarzmann-Wachmann, a comet that fragmented repeatedly throughout the early 2000s. Its pieces now occupy a vast section of its orbit, and Earth has occasionally passed through this debris stream, producing meteor showers. Though most fragments are small, some are large enough to survive atmospheric entry. Even more mysteriously, Comet Biela in the 1800s split into two distinct pieces. By the time it should have returned again, it was gone, dissolved into a meteor storm that lit up the skies across Europe and North America. What was once a comet had become a storm of fire overhead. These events remind us, not every comet completes its journey intact. Some end their lives in the atmosphere of planets. Others disintegrate quietly, leaving behind remnants that Earth encounters unexpectedly. As we watch Comet Swan, astronomers are asking critical questions. Is its instability a precursor to fragmentation? Could it create a debris trail capable of intersecting Earth's orbit? Is this comet part of a cycle, perhaps returning now with renewed activity after previous disintegration events we no longer remember? History tells us that comets transform. They break. They scatter their remains across the solar system. And every time one begins to act strangely, as Swan now is, we are not only observing a comet, we are witnessing a pattern repeat itself. A pattern written not in myth or fear, but in the quiet language of cosmic cycles, reminding us that the past is never truly gone. It simply waits among the stars. Its emerald halo is not just beautiful, it signals the presence of diatomic carbon and cyanogen, building blocks of organic chemistry. In this comet, we may be witnessing the ingredients of life itself. The glow that surrounds Comet Swan is unlike ordinary light. It is not reflected sunlight bouncing off dust, nor the glow of simple ice turning to vapor. It is the radiance of chemistry, of atomic bonds breaking, of molecules reacting in the vacuum of space. When ultraviolet radiation from the sun strikes the gases streaming from the comet's nucleus, a transformation occurs. Carbon-based molecules, locked in ice since the birth of the solar system, break apart and fluoresce, emitting a soft green light that surrounds the comet like a luminous aura. This glow is more than a visual spectacle. It is a clue. Diatomic carbon, C2, and cyanogen, Cn, both detected in Swan's coma, are not random materials. They are the precursors of more complex organic molecules, substances that can act as the seeds of life when delivered to a planet's surface. Billions of years ago, Earth was bombarded by comets similar to Swan. Each impact delivered water, ammonia, methane, and carbon-rich compounds, substances that, when mixed in the crucible of a young Earth, may have helped ignite the chemistry that led to life. What we are witnessing now in Comet Swan is the same process, unfolding before our very eyes. The green color is not just a byproduct of ionization. It is a signal from deep time. It tells us that beneath the comet's crust lies a reservoir of organic material, frozen in place since before Earth existed. Every puff of gas, every stream of dust is a message carried across tens of thousands of years. This is what the early solar system was made of. Other comets have glowed green, notably Comet McNaught and Comet Lovejoy. But Swan's emerald aura is distinct in its extent and intensity, suggesting a particularly large concentration of carbon-bearing compounds. These molecules could be remnants from interstellar space, captured during the formation of our solar system. Some theories propose that comets like Swan are not just messengers, but couriers, carrying the raw materials of biology between worlds. Within the tail of this comet, scientists detect volatile organics that decompose into simpler forms under solar radiation. These react further, forming complex chains, precursors to amino acids. If fragments of the comet fall toward Earth or interact with our atmosphere, those molecules could undergo yet another transformation, continuing a chemical journey that began in the darkness of the Oort cloud and could end in the oceans of a living planet. And here lies the wonder. Comet Swan may never strike Earth and likely never will, but collision is not required for influence. Its dust will linger in the solar system long after the comet itself returns to the void. Over time, Earth will inevitably pass through regions of space marked by its passage. Microscopic grains could fall gently through our atmosphere, descending into clouds, oceans, and soil. Within those grains may lie the same molecules that once helped spark life on Earth billions of years ago. This is not speculation. It is part of a growing scientific understanding that life's building blocks are not unique to Earth, but widespread across the universe. And so, as we watch the green glow of Comet Swan, we are not only seeing a comet, we are seeing a mirror held up to our own origins, a reminder that the story of life did not begin on Earth. It began among the stars. Ground-based telescopes fail to detect it because optical surveys are limited by the glare of the sun. Swan used that glare as a cloak, only revealing itself after it had already passed perihelion. In the great network of planetary defense, we often imagine omniscience, eyes pointed in every direction, instruments endlessly sweeping the heavens for any object that dares to draw near. But the truth is far more fragile. Our detection systems are powerful, yes, but they are not omnipotent. They are bound by physics, position, timing, and our own assumptions about where dangers are most likely to appear. Comet Swan slipped past our defenses not because it was invisible, but because it was hiding in the one place we were not looking. The sun, the brightest object in the sky, illuminates our world but blinds our telescopes. Ground-based optical surveys, such as Pan-STARRS, Atlas, and the Catalina Sky Survey, cannot observe regions too close to the sun's position in the sky. The intense glare of sunlight scatters through Earth's atmosphere, overwhelming faint objects. Even space-based telescopes like Hubble or James Webb do not point near the sun, as doing so would endanger their delicate sensors. Comet Swan approached precisely through this blind zone, the solar glare corridor, a region where any object remains hidden until it has already swung around the sun and begun its outward journey. By the time Swan emerged into observational view, it had already completed its most active informative phase, its perihelion passage. We did not see it when it was brightest. We saw it during its exit. It is like discovering a ship only after it has passed through the fog, hearing only the wake of its motion rather than witnessing its arrival. Adding to the mystery is how Swan was discovered, not by optical light, but by ultraviolet. The Swan instrument aboard the SOHO spacecraft is not designed to hunt comets. It monitors hydrogen in the solar wind. When Comet Swan began to outgas intensely near the sun, its sublimating ice released massive clouds of hydrogen. It was a chemical flare, not a visual one. Had Swan not been this volatile, had it been slightly smaller, slightly less active, it might never have been noticed at all. Even now, scientists acknowledge that we likely missed weeks, perhaps months, of early activity. We do not know what the comet's nucleus looked like before perihelion. We do not know if it fragmented, if it outburst multiple times, or if its orbit shifted subtly due to asymmetric gas jets. Our models are built on partial information, and that uncertainty is not just an observational inconvenience. It is a reminder of our vulnerability, because what happened with Comet Swan is not an isolated anomaly. We have witnessed this before. Comet McNaught in 2007 appeared suddenly out of the solar glare, already spectacular by the time we saw it. The sun-grazer comets discovered by SOHO often erupt into brilliance only after they become visible to ultraviolet instruments. Some do not survive their solar encounter. Others endure and emerge, changed. If a comet should one day take a similar path but with a slightly altered trajectory, one aligned not just with Earth's orbit, but with Earth itself, we might not know until it is too late to react. This is not fear. It is truth. The cosmos is still full of places where giants can hide. And Comet Swan showed us just how easily the next one might already be on its way. Finding a comet on its way out of the solar system means losing critical data about its behavior at closest pass. That means one thing. We are now watching a story already in motion, missing the opening chapters. In astronomy, timing is everything. To observe a comet before it reaches its closest point to the Sun, its perihelion, is to witness its awakening. This is when it begins to shed its icy skin, revealing its true nature. It is when jets of gas erupt from beneath the surface, when brightness intensifies, when tail formation begins, and when fragmentation is most likely to occur. But Comet Swan was not discovered during this vital window. By the time we saw it, that chapter had already closed. The comet had already encountered the Sun's furnace. It had already begun reacting, expanding, possibly breaking, and we do not know exactly what happened. Without early discovery, astronomers are left with consequences instead of causes. We can see the comet's coma expanding, but we do not know when it began. We can measure its current outgassing, but we do not know its peak. We can detect hydrogen in ultraviolet, but we cannot determine how much water ice was lost during its closest solar encounter, or whether that loss was smooth or violent. In other words, we are studying echoes, not events. By missing the approach phase, we lost precious data about the comet's original brightness curve. This curve can reveal the size of the nucleus, the number of active regions on its surface, and even the comet's rotational speed. It's the difference between watching a volcano erupt from the beginning and walking into the ash cloud hours later, trying to guess how large the eruption was. This late discovery also means we missed the earliest chemical signatures. As comets approach the Sun, different ices vaporize at different temperatures. Carbon dioxide sublimates first, followed by water ice, and then more complex organic materials. The order and rate of these emissions tell us about the comet's composition, whether it is rich in primordial volatiles or more processed from past solar encounters. We did not see that sequence unfold. All we have now is aftermath. Worse still, when comets undergo internal stress near the Sun, they sometimes fracture silently. These fractures can create debris fields that drift slightly ahead of or behind the main nucleus. If such fragmentation occurred before we detected SWAN, we may not yet be aware of the fragments. They could be traveling near the comet, undetectable for now, only to reveal themselves later as separate bodies or meteor streams. This lack of early observation leads to uncertainty in orbital predictions. Without precise measurements during perihelion, non-gravitational forces like asymmetric outgassing cannot be accurately modelled. That means predictions about future paths carry wider margins of error. It also means we cannot fully anticipate how much the orbit might evolve over time, or what debris may be left behind for Earth to pass through later. But perhaps the most profound impact of this late discovery is not scientific. It is philosophical. When we miss the beginning of a comet story, we are reminded that the universe is not on our schedule. We are observers, not authors. We watch as ancient travelers appear suddenly, already transformed by journeys we were never witness to. And so, with Comet Swan, we do not begin at the beginning. We join the story mid-sentence. The question now is not how the story started, but how it will end. As Comet Swan nears Earth, our planet is entering the debris stream of another comet, Halley, creating a meteor shower overhead while a new comet rises silently below. In the unfolding drama of the night sky, timing is rarely accidental. While Comet Swan approaches from the dawn horizon, another ancient traveller is already speaking through light. Comet Halley, or rather, the remnants it left behind tens of thousands of years ago. Each October, Earth drifts through this debris field, and the Orionid meteor shower ignites the heavens, streaks of light racing across the upper atmosphere, glowing white and blue as grains of comet dust, no bigger than seeds, vaporize at 66 kilometers per second. Above us, fire in the sky. Below the horizon, just before dawn, the rising glow of Comet Swan. Two cosmic events converging in a single week, one ancient, one unexpected. This is not just a coincidence of beauty. It is a moment of profound resonance, where the sky becomes a stage for understanding how comets write their legacy, not in singular visits, but in the trails they leave behind. Comet Halley is not here. Yet its presence is everywhere, in every meteor that falls, in every streak that vanishes as quickly as it appears. Its body vanished into the void centuries ago, but its influence remains woven through Earth's orbit. They remain. Now, as Earth looks upward to the Orionids, our awareness is being drawn back to comets. Back to these cosmic messengers that cross our skies to tell us of distant realms and ancient origins. Yet even as we marvel at Halley's remnants above, a question lingers behind us. What of the comet that is here now? What of the one not in memory or meteor, but in motion, alive, active, and drawing closer? Comet Swan is not intersecting Earth's path during this passage, but it is laying one down. As it sheds material into space, that material begins its own journey, stretching along the comet's orbit like threads of fate. One day, Earth may cross that stream, just as we cross Halley's today. The Orionids are not merely a meteor shower, they are a glimpse into Earth's future interactions with objects like Swan. And as astronomers point their telescopes toward the familiar Orionids, they do so knowing that another story is unfolding below the horizon. Swan, though fainter than the meteors blazing overhead, is far closer. It is not merely remnants of a long-ago passage. It is an active force reshaping space around it right now. This overlap of events presents a moment of contrast. Above us, the quiet beauty of cometary legacy, predictable, cyclical, poetic. On the horizon, the emergence of a comet whose legacy is still unwritten, unstable, unpredictable, alive. In ancient times, cultures would look to the sky and speak of omens when such convergences took place. Two celestial signs appearing at once meant something was shifting. Worlds were aligning, cycles overlapping. Today, we do not speak of omens. We speak of orbital dynamics. Yet the feeling is the same. A doorway has opened in the heavens. One comet reminds us of what was. Another asks us to consider what may yet be. The Orionid meteors will fade come morning. But Comet Swan will continue upward, climbing the sky, asking silently, what legacy will it leave behind? 2 comets and a meteor shower all in 1 week. Skywatchers are delighted, but scientists are wary. Rare overlaps often hide greater stories. In the world of astronomy, celestial events are usually spaced across seasons or years, each one receiving the full gaze of telescopes, instruments, and human attention. But every so often, the sky becomes crowded. Objects that normally dominate headlines alone arrive simultaneously, sharing the heavens like actors competing for the same stage. To the casual observer, this is a marvel, a festival of light. But to those who track orbital mechanics and space weather, such overlaps are not merely beautiful, they are distracting. In the same week that Comet Swan approaches its closest point to Earth, Comet Lemon became visible in the northern hemisphere, brightening steadily and drawing its own wave of public interest. Meanwhile, the Orionid meteor shower reaches its annual peak, raining debris from Halley's comet across the sky. The media calls it a celestial celebration. Headlines focus on the wonder, the beauty, the rarity of such alignments. But in scientific circles, a different conversation is taking place. Comets are not just spectacles. They are dynamic, active bodies that shed mass, fragment under stress, and alter their orbits under the influence of solar radiation. The presence of multiple comets in the sky at once is not an omen, but it is an indicator of changing conditions in the inner solar system. Increased cometary activity could be the result of gravitational perturbations in the Oort cloud, the shifting influence of Jupiter's orbit, or simply a statistical clustering of long-period objects entering the inner solar system within the same time frame. Yet the concern is not about coincidence. It is about attention and allocation of resources. Astronomers have limited telescope time. Large observatories book schedules months or years in advance. When the sky becomes crowded with transient phenomena, decisions must be made. Which object gets priority? What data is lost from the one we do not observe as closely? Comet Swan, arriving unexpectedly and only detectable after its perihelion, already suffered from a lack of early observational data. Now, its monitoring must compete with objects that are, frankly, easier to study. The Orionids dominate public discussion, capturing imaginations with bright meteors anyone can see without equipment. Comet Lemon captivates astrophotographers, its long tail and predictable orbit making it a reliable subject. Swan, by contrast, is unpredictable, newly active, and potentially unstable, yet getting less public attention precisely because it is less visible to the naked eye. This overlap of distractions also extends to media narratives. While attention is fixed on 3i Atlas, the interstellar celebrity with no threat to Earth, Comet Swan has slipped into our neighborhood with a much smaller margin of distance. The public fascination with the exotic blinds many to the reality that the familiar may be far more relevant. It is not that the other comets or meteor showers are unimportant. They are wondrous. They remind us of our place in a living cosmic system. But they create noise, a shimmering veil of beauty that can obscure the urgent questions beneath. Questions like, how active is Comet Swan becoming? Has it already begun to fragment? Are we accurately modelling its non-gravitational acceleration? What debris is it leaving behind? In a sky full of distractions, it becomes easy to forget that some objects do not simply pass. They transform everything around them. And Comet Swan is not here to perform. It is here to change the story. We do not know its core size, its rotation, its stability, or whether it has already begun to shed fragments. And in astronomy, what we do not know is often what matters most. The mystery of Comet Swan is not rooted in what we see, but in what remains hidden. Every new observation deepens the questions rather than answering them. Its coma, glowing with hydrogen and carbon, tells us it is active, but not how active it was before we detected it. Its tail stretches across millions of kilometers, but tells us nothing about the precise shape or structure of the nucleus at its heart. Our instruments can read its motion, but cannot yet decipher whether that motion is smooth and stable or the beginning of chaos. We do not know its size. Estimates range anywhere from a few kilometers to over 10, but those numbers are based on coma brightness and assumptions about reflectivity. A dark nucleus could be massive yet appear modest. A reflective nucleus could be small yet appear bright. We do not know the precise spin rate. Some comets rotate slowly, gently turning their active faces toward the sun. Others spin rapidly, their surfaces cracking from centrifugal force, hastening fragmentation. Swan's outbursts may indicate rotational instability, but without direct visual measurement, we can only infer. We do not know if it has fragmented already. The fluctuations in brightness could be signs of internal venting, or signs that pieces have already broken off. These fragments, if they exist, might be too small to detect now, but large enough to matter later. A 1-kilometer chunk of ice and rock, drifting slightly ahead or behind the comet, could follow a slightly different path, close enough that Earth may pass through its debris stream in months or years to come. We do not know how outgassing is influencing its orbit. Comets do not travel like asteroids. They breathe. Each jet alters the path minutely, making long-term predictions difficult. Our current models incorporate gravitational forces well, but non-gravitational forces remain uncertain. A strong outburst could nudge the nucleus into a different trajectory, reducing or increasing the margin of distance during close approach. We do not know the true composition of its ices. Are they mostly water, or dominated by carbon monoxide, carbon dioxide, ammonia, or methane? Each of these volatiles sublimates at different temperatures, producing different behaviors. A water-dominated comet brightens primarily at perihelion. Swan's activity profile does not match a simple pattern. We do not know the shape of its orbit on its return journey. Long-period comets are heavily influenced by giant planets such as Jupiter. A gravitational encounter, however slight, could alter its period dramatically. What appears now to be a 22,000-year orbit could, after passing near Jupiter, become a 5,000-year orbit, or never return at all. But perhaps the greatest unknown is also the simplest. Why now? Why did this comet awaken at this moment in human history? Just as our observational capacities have expanded, just as our awareness of cosmic fragility has grown, we do not assign purpose in science, but we recognize patterns. And Swan has emerged not as a silent traveler, but as a messenger from the edge of time. What we know of it is fascinating. What we don't know may be transformative, and the answers are approaching us now, riding on a tail of ice and fire through the dark. Every comet is a recorder of history, untouched by planetary forces, unchanged since the birth of the solar system. Swan is not a rock, it is a memory. Imagine holding in your hands a fragment of time, unchanged, unweathered, pristine in its composition since the dawn of our star. This is what a comet truly is. Not merely an object that moves through time, but an object that carries time with it. While planets like Earth have reshaped themselves through volcanic eruptions, tectonic shifts, erosion, and biological evolution, comets have done none of these things. They have been preserved, frozen memories drifting through the deep cold of the outer solar system. Comet Swan is one such memory now, passing near enough for us to witness it before it returns to the darkness. In its nucleus lie materials older than Earth's continents, predating the oceans, the atmosphere, even the formation of the Moon. These ices and dust grains are remnants from the original solar nebula, a swirling cloud of gas and debris that collapsed under gravity to form the Sun. Before planets were born, the first solids condensed into microscopic grains, covered in ices, and coated in organic molecules created by radiation in the interstellar medium. Over time, these grains clumped together into larger bodies, forming the seeds of comets. Where planets underwent intense transformation, comets like Swan did not. They were ejected to the far edges of the solar system, into the Oort cloud, where temperatures hover near absolute zero and gravitational interactions are minimal. In this frozen exile, they remained unchanged until gravity summoned them back. As Swan approached the Sun, its icy surface began to vaporize, releasing gases that had been trapped within it for over 4 billion years. Instruments studying its coma are not just observing a comet's current state. They are analyzing ancient chemistry, unlocking clues about the building blocks that seeded our own world. Within that vapor are traces of water that may match the isotopic composition of Earth's oceans, carbon compounds that could have contributed to prebiotic chemistry, and noble gases that reveal the environment of the early solar nebula. In this way, Swan is more than a comet. It is a moving archaeological dig, one that reveals its secrets not through excavation but through evaporation. Cometary scientists often refer to comets as dirty snowballs or icy dirt balls, but these playful terms disguise their profound significance. Comets are libraries, each one containing a different story from a time before life began. Swan offers an especially rare opportunity because it is a long-period comet, likely visiting the inner solar system for the first time since the Paleolithic age. It has not been baked by repeated passes around the Sun. Its volatile ices are fresh. Its structure is likely pristine. It is not a veteran of the inner solar system. It is a first-time traveller returning to show us what has been preserved in darkness. To look upon Comet Swan is to look backward in time, to witness the materials from which Earth was formed, to see the unaltered ingredients that once drifted in a nebular cloud before coalescing into a world capable of life. And in doing so, we are reminded, we are not separate from the cosmos. We are its continuation. Comet Swan is a memory not of something lost, but of where we began. 22,000 years ago, when this comet last visited, Earth was in an ice age. Humans walked alongside mammoths. The last time it passed, our ancestors looked up in awe. Try to imagine the world as it was then, not the world of cities and satellites, but a world of ice and silence. Glaciers stretched across continents. Seas were lower, exposing land bridges across which early humans migrated. Volcanoes rumbled in the distance. Herds of mammoths roamed across frozen plains beneath a sky untouched by artificial light. where every star shone like a diamond in the cold, and far above them, emerging from the darkness of space, a streak of green light appeared on the horizon. They did not call it Comet Swan. They had no telescopes, no observatories, no scientific understanding of orbital mechanics. But they had eyes, minds, myths. They saw this same visitor, a glowing apparition with a tail stretching across the heavens, and they did what humans have always done. They told stories. In the Paleolithic world, the sky was the realm of the divine. Comets were not merely objects, they were messages. Some cultures believed them to be celestial serpents, slithering across the stars. Others saw them as torches carried by sky spirits. To some, they signaled change, an omen of famine or fortune, a sign that the balance of nature had been altered. As Comet Swan appeared in those ancient skies, its tail would have lengthened night after night, growing brighter as it neared the sun. Tribes would have gathered to witness its ascent. Around campfires, they may have spoken its meaning in hushed tones, believing it to be a sign that the sky itself was alive. Unlike planets, which wander slowly across the horizon, comets move with noticeable speed, changing position night by night. Ancient people, who lived in daily conversation with nature, would have noticed. They might have marked its path on cave walls. In fact, archaeologists have found Paleolithic drawings that some believe to represent comets, lines, and points etched in ochre, with trailing arcs suggesting tails. These images, found in sites across France and Spain, may well be humanity's earliest astronomical records. And now, tens of thousands of years later, that same celestial visitor has returned. Not to a world of ice, but to a world of light, where cities glow brighter than stars, where humans no longer walk with mammoths, but with machines. Yet the comet is unchanged. It follows the same path it traced long before history. It carries the same materials it carried then, frozen in time. This realization is profoundly humbling. Comet Swan is not just passing by, it is completing a journey that began long before us and will continue long after. Its orbit is a reminder that our species is a moment in cosmic time. We are not the observers of this universe. We are participants in its story, arriving for one brief chapter. And as Swan crosses the sky once more, we are connected to every human who has ever lifted their gaze in wonder. We are watching what they once watched, asking what they once asked. What does it mean? Where did it come from? And most of all, will it return again, long after we are gone? Even our most advanced instruments cannot guarantee certainty. We rely on models, probabilities, and limited data points. The truth is still unfolding, one observation at a time. Science is not a monument of answers, it is a process of questions. We study celestial objects not with perfect vision, but with careful inference. Every reading, every measurement, every plotted orbital path is built from transient signals, photons captured in the brief moment they touch our instruments, radio pulses echoing from distant receivers, mathematical models predicting behavior based on what should happen. But comets like Swan remind us that nature rarely conforms to what should be. It behaves according to what is, and what is often lies beyond our immediate grasp. The rise of Comet Swan has highlighted a simple truth. Much of what we think we know rests on incomplete data. We did not see the comet before perihelion. We missed its initial outbursts. We do not have high-resolution images of its nucleus. Our understanding is built from what we can observe, its brightness profile, its tail structure, its hydrogen emissions. But these observations are not a narrative. They are fragments, clues. When we build models from these clues, we must make assumptions about the comet's size, its composition, its spin, its activity. Yet every assumption introduces uncertainty. A model can show that the comet should fade at a certain distance from the Sun. But Swan is growing brighter. A model can show that its path should remain stable. But outgassing is altering its trajectory. Each new observation forces us to revise our understanding, sometimes subtly, sometimes dramatically. This is not failure. This is the essence of scientific discovery. But it is also humbling, because it means we do not predict the cosmos with certainty. We chase it. With each night of observation, our telescopes capture just a sliver of the truth, one frame in a story still unfolding. From those frames, we attempt to understand the whole. And yet, in this uncertainty, humanity finds hope. Not because uncertainty is comforting, but because uncertainty is possibility. It means the story is still alive. It means we are not merely witnessing, but discovering. Consider how many times science has been surprised by comets in the past. Comet Holmes exploded in 2007, brightening by a factor of nearly 1 million in just hours. Comet Shoemaker-Levy 9 tore itself apart under Jupiter's gravity. Comet Lovejoy survived a dive through the Sun's corona when it was expected to disintegrate entirely. Again and again, comets break the rules we set for them. So we do not place our faith in any one model or any one prediction. We place it in our capacity to observe, to adapt, to learn. Comet Swan is not a threat we can quantify, nor a spectacle we can control. It is a messenger, delivering not certainty, but insight. And insight must be earned through patience, through humility, through the acceptance that knowledge is not a destination, but a path we walk one step at a time. The fragility of hope in data is not weakness. It is the quiet strength of knowing that truth is still ahead of us, waiting to be revealed in the light of a comet's passing. If Swan has already shed fragments, they could be invisible, until Earth passes near them. In space, a kilometre-wide fragment can remain unseen until it is only days away. When we think of danger from space, we often imagine a single massive object, a comet or asteroid, a solitary threat on a direct collision course. But the cosmos is rarely that simple. Comets do not always travel alone. They fracture, they shed pieces, and those pieces, bound by gravity yet nudged apart by gas jets and sunlight pressure, can become separate bodies, each with its own destination. These fragments are often small, dark, and silent, invisible until they reveal themselves through reflected sunlight or by entering our atmosphere. Comet Swan has already shown signs of internal instability. Sudden outbursts, fluctuations in brightness, a growing coma beyond expected models. These could be prelude to fragmentation. If that fragmentation has already begun, the pieces may have drifted slightly ahead or behind the nucleus, hidden in the haze of released dust. They are not yet independently visible, but that does not mean they are not there. Astronomers have long known that fragmentation is a natural phase in a comet's lifespan. Some comets break dramatically, scattering their remains in a single catastrophic event. Others fracture slowly, silently, shedding pieces the size of cars, houses, or mountains. These fragments can follow nearly the same path as the parent body, nearly, but not exactly. Each one experiences outgassing differently, altering its trajectory. Over time, the distance between fragments can grow from hundreds of meters to millions of kilometers. Some fragments remain dormant, absorbing sunlight without outgassing. These dark bodies, rich in carbon compounds, are effectively invisible until they come perilously close. They do not develop comas. They do not shine. They drift through space like shadows. This is why fragments matter, because it is not the comet we see that poses the only question. It is the comet we do not. In recent years, several near-Earth objects were discovered only after passing dangerously close, not because our telescopes failed, but because those objects were small, dark, and silent. A fragment just half a kilometre across could go unnoticed until it was already near Earth's orbit. A fragment 1 kilometre wide, comparable to the impactor believed to have caused the Younger Dryas event, might be visible only days in advance if approaching from the direction of the Sun. And Comet Swan came from the Sun's glare. Its offspring would emerge the same way. Even if no large fragments exist, there is another reality to consider. Dust and ice released by SWAN form what astronomers call a meteoroid stream, a ribbon of debris stretching along its orbit. Earth may not pass directly through that stream on this approach, but the stream remains in space indefinitely. Over years, decades, or centuries, gravitational interactions with planets, especially Jupiter, could gradually alter SWAN's debris into an Earth-crossing trail. That is how meteor showers are born. That is how meteor storms are born. Today's comet is tomorrow's rain of fire. In the silent gulf between planets, fragments drift unseen. They carry no warning. They emit no signal. They are shards of an ancient traveler slowly unwinding its story through space. And somewhere in that darkness, a piece of Comet SWAN may already be waiting, its path unknown, its nature hidden, until gravity and time reveal what the comet itself has left behind. Humans respond more strongly to mystery than certainty. SWAN's threat is not defined. That's what makes it so compelling and unsettling. Fear, in the human mind, is rarely born from what we see. It emerges from what we almost see. From the shapes in the darkness, the sounds we cannot identify, the outcomes we cannot predict. In the modern world, we are accustomed to certainty. Weather forecasts predict storms days in advance. Economic models map global markets. Medical scans peer inside our very cells. We have grown used to living within a bubble of knowledge, where uncertainty feels unnatural. And yet, every so often, an object like Comet SWAN arrives, reminding us that uncertainty is the true fabric of the universe. What makes SWAN different from other celestial events is not what is known, but what is unknown. It is not the comet's current path that stirs unease, it is the margin of error. It is not the visible tail that generates tension, it is the possibility of invisible fragments. It is not the present that disturbs the subconscious, it is the implied future. Humans are storytellers by nature. Where there are gaps, the mind fills them. Ancient civilizations looked up at comets and saw omens. They associated these fiery visitors with kings rising and empires falling, not because comets caused these events, but because comets appeared when the world was changing. Today, we no longer connect comets to prophecy, but their presence still triggers something primal. A cosmic visitor arriving unannounced speaks to our deepest instincts. We do not control the sky, and the sky is watching us. Psychologists call this pattern seeking under uncertainty. When faced with a potential threat we do not fully understand, our brains elevate its significance. It is the same reason we fear turbulence on a plane more than the drive to the airport, even though the latter is statistically more dangerous. Comet SWAN, with its unknown nuclear size, unpredictable activity, and mysterious outbursts, activates that ancient circuit in the mind, the one designed to keep early humans alive when danger lurked beyond the firelight. There is also the allure of the sublime. Celestial fear is not only about danger, it is about awe. The sight of a comet is a reminder that we inhabit a small island in a cosmic ocean, that somewhere, beyond the reach of our technologies and languages, forces beyond comprehension are in motion. This is not terror, it is reverence, a recognition of our place within something unimaginably vast. But in that vastness lies vulnerability. The rise of misinformation in the digital age further magnifies this feeling. Social media amplifies uncertainty. Speculation spreads faster than verified data. A single headline, "Comet approaches, closer than expected," becomes fuel for imagination. Each person adds their own interpretation. Each interpretation creates new fear. It is not the comet itself that becomes the source of anxiety, but the ever-changing story around it. Comet SWAN is not a doom-bringer. There is no evidence that it poses a direct threat to Earth in this passage. Yet the possibility of fragmentation, the potential for future debris intersections, and our limited knowledge ignite a sense of cosmic suspense. It is the fear of what might be, not what is. And in that sense, Swan is not just a comet. It is a mirror, reflecting not just sunlight but our own psychology, our longing to know, our fear of the unknown, our curiosity, our vulnerability. The skies do not frighten us because they are hostile. They frighten us because they are mysterious. And the appearance of Comet Swan has reopened the oldest question humanity has ever asked when looking up. What else is out there? And what is it trying to tell us? We once watched a comet tear itself apart and crash into Jupiter with force equivalent to millions of nuclear weapons. That was a warning from nature. Comets do not simply pass by, they can erupt. In July of 1994, the world witnessed something no human had ever seen before. Through telescopes scattered across Earth and in orbit, astronomers watched as pieces of a broken comet, Shoemaker-Levy 9, plunged into the atmosphere of Jupiter one after another. Each fragment entered at speeds of over 60 kilometers per second, igniting enormous fireballs that rose higher than the diameter of Earth. The explosions were so powerful that they left dark scars in Jupiter's atmosphere, visible for months. It was a moment that transformed comet science forever. Before Shoemaker-Levy 9, many had viewed comets as passive wanderers. Beautiful, yes, but ultimately harmless. They were icy relics, spectacular to behold but irrelevant to planetary dynamics. That illusion vanished in a series of violent impacts that revealed the true nature of comets. They are fragile, unstable, and capable of catastrophic transformation. The story of Shoemaker-Levy 9 began 2 years earlier, when the comet passed too close to Jupiter. Caught in the gas giant's immense gravitational field, it was torn apart. Its nucleus fractured into more than 20 distinct pieces, each now following a death spiral toward the planet. As the fragments descended, astronomers realized they had a once-in-a-lifetime opportunity to watch a comet die. The impacts released more than 6 million megatons of energy, far beyond the power of Earth's entire nuclear arsenal. For days, Jupiter seemed to shudder with aftershocks. What made this event even more sobering was the realization that if Jupiter had not been there, acting as a gravitational shield, those fragments could have remained on solar system crossing trajectories, perhaps even intersecting Earth's orbit in future centuries. Shoemaker-Levy 9 was not just a cometary event, it was a warning. It showed us that comets can break apart suddenly, unpredictably. That fragmentation is not a slow process, but a violent one, and that when a comet fractures, its pieces do not simply vanish. They become new objects, new threats, new stories written into the gravitational symphony of our solar system. Comet Swan is not Shoemaker-Levy 9. It is not expected to plunge into a giant planet, but it is showing signs eerily reminiscent of early fragmentation. Sudden outbursts, fluctuating brightness, a growing coma. These are the same signatures that preceded Shoemaker-Levy 9's disintegration. The lesson we draw is not one of fear, but of awareness. We are watching a living body in motion. A comet is not a static object, it is a process. Just as Shoemaker-Levy 9 taught us that comets can be cosmic torches, igniting firestorms in the atmospheres of planets, Comet Swan may be teaching us a quieter lesson, that a comet does not have to hit a world to affect it. The fragments it leaves behind may drift silently through space, waiting for centuries until a planet crosses their path. The universe does not operate on human timescales. A comet fragmented today may write its true story thousands of years from now. Shoemaker-Levy 9 showed us that to ignore a comet is to underestimate it. Comet Swan reminds us that to underestimate what might happen is to forget the lesson written across the skies in 1994. Comets are not visitors. They are forces of change. Even a mild fragmentation event could create a field of debris that Earth may encounter weeks or months later, each piece following a slightly different path. Fragmentation is not a rare accident in the life of a comet. It is an expectation. Comets are among the most fragile objects in the solar system, held together not by strength or solid rock, but by weak gravity and frozen bonds between particles that have never known heat. When they pass near the Sun, these bonds strain, they crack, and sometimes they break altogether. We have seen this countless times in the historical record, and now, with Comet Swan showing signs of increasing instability, astronomers are beginning to ask a critical question. What if Swan splits? The first thing to understand is that fragmentation is not a singular event, it is a continuum. A comet may shed dust, then boulders, then entire segments of its nucleus. Some splits are catastrophic, like Shoemaker-Levy 9, which shattered into more than 20 major fragments. Others are subtle, producing companion fragments that gently drift apart over time, only detectable through changes in brightness or rotational dynamics. If Swan were to split, one outcome is virtually certain. Its debris would not disappear. Instead, it would begin to spread along its orbital path, forming a debris stream. Earth may not be in the path of that debris immediately, but over time, gravitational forces, especially from Jupiter, could alter the fragment's orbits just enough that they begin to intersect Earth's orbit in subsequent years or decades. This is how meteor showers are born. But if the fragments are large, tens or hundreds of meters in diameter, then Swan's breakup could eventually produce meteor storms capable of lighting up the sky with thousands of fireballs per hour. And if any of the fragments are kilometers in scale, their long-term trajectories would become objects of intense interest to planetary defense agencies. A fragment of that size, if perturbed into an Earth-crossing orbit, would represent a serious impact hazard. Perhaps not now, not in our lifetimes, but in the centuries to come. The moment of fragmentation itself may be silent. There would be no explosion we could hear from Earth. Instead, astronomers would see a sudden increase in brightness, multiple condensation points within the coma, or unusual changes in the shape of the tail. These signs could appear overnight, and once they do, the clock begins to change, not for immediate danger, but for long-term consequences. A splitting comet becomes a new kind of celestial entity. Not a single traveller, but a fleet, and each fragment carries its own destiny. Will the pieces stabilize and remain inert, slowly fading as they drift back into deep space? Or will internal gases continue to drive outgassing, altering their paths more aggressively than the parent body? If Swan splits, it will not be the end of the story. It will be the beginning of many stories. Each fragment a new question written into the solar system. The Earth's orbit will continue as it always has, circling the Sun year after year. But if fragments of Comet Swan begin to populate that path, Earth will eventually meet them. Whether that meeting is marked by sparks of light in the upper atmosphere, or by something that reaches the ground, will be determined not by fate, but by physics. And the physics is already in motion. As it moves farther from the Sun, the comet should begin to fade. But if it brightens again, it will mean something is changing beneath its surface. A comet's journey past the Sun is not a singular moment, it is a transformation. As Comet Swan travels away from its closest solar approach, logic tells us its activity should decrease. Less heat means less sublimation. Less sublimation means a shrinking coma, a fading tail, a gradual return to dormancy. And yet, in the case of long-period comets like Swan, the story is rarely so simple. Some comets, after appearing to fade, suddenly surge back to life, brightening unexpectedly, producing new jets, or even fragmenting under delayed thermal stress. If Swan brightens again in the months following its perihelion passage, astronomers will know this is not the end of its awakening. It is the beginning of something deeper. When a comet first approaches the Sun, only its surface ices are activated. But as heat penetrates deeper into the nucleus, it reaches subsurface ices that have remained sealed away for tens of thousands of years. These pockets of volatile material, carbon monoxide, carbon dioxide, methane, ammonia, are far more energetic than surface water ice. They do not need direct sunlight to activate. Once heat reaches them internally, they can trigger explosive outbursts even as the comet is moving away from the Sun. This is the critical phase we are entering now. Comet Swan is leaving the inner solar system, but heat continues to move inward through its layers. The crust, weakened by earlier activity, may be developing new fractures. These fissures can expose fresh ice. The comet may appear quiet, only to flare unexpectedly as trapped gases burst outward. Astronomers refer to this phenomenon as delayed outgassing. In some historical cases, these delayed reactions were more intense than those seen at perihelion. They triggered fragmentation events that permanently altered the comet's orbit. If Swan experiences such a secondary awakening, its trajectory could shift. Its rotational speed could increase, and its nucleus could begin to disintegrate. This is why Swan's next solar encounter is not limited to its physical proximity to the Sun. It is unfolding internally, within the heart of the comet itself. And there is another consideration. Though Swan is now receding from the Sun, it will continue to move through gravitational fields of the inner solar system. If it passes anywhere near Jupiter, Saturn, or even Mars, those planets could perturb its orbit ever so slightly. A small gravitational nudge, combined with non-gravitational acceleration from outgassing, could significantly alter its return path. The difference between a 22,000-year orbital period and a 5,000-year one could come down to a single encounter. Thus, astronomers are preparing not just to observe Comet Swan's departure, but to monitor its behavior long after it has faded from public view. If it brightens again, it signals structural instability. If it fragments, it creates a new population of celestial bodies, each needing tracking. If it remains active longer than expected, the materials within its core will tell us more about its composition and its future. In cosmic time, this passage is only a moment, but what happens next could determine whether Comet Swan is gone for tens of millennia, or whether it will return far sooner. Its next encounter with the Sun may not be measured in distance. It may be measured in destiny, written now, within its awakening core. Some civilizations saw comets not as threats, but as messages, reminders that the heavens are alive. Whether omen or opportunity, Swan calls us to attention. Since the dawn of time, comets have served as celestial punctuation marks, appearing unexpectedly in the sky, breaking the silence of the stars, and reminding humanity that the universe is not static. Ancient cultures saw these cosmic visitors as divine communications. Not always warnings, though often misunderstood as such, but signals, reminders, moments designed not to instill fear, but awareness. To the Persians, comets were the mouths of the heavens, speaking truths that could not be conveyed in words. In China, scribes recorded their appearances meticulously, tracking correlations between comets and dynastic changes, not because the comet caused the change, but because it signified a moment of transition. The Maya saw them as sky serpents, slithering between realms, bridging the mortal and the divine. Even in medieval Europe, where comets were often depicted in paintings of biblical scenes, their role was not always doom. It was revelation. They were symbols of things being uncovered. In that sense, Comet Swan arrives not as a threat, but as a messenger. A messenger reminding us of our origins. A messenger calling us to look up, not down. Not just to predict, but to wonder. Its very appearance forces us to confront deep truths about our place in the cosmos. We are not separate from the universe. Observing from the outside, we are within it, made of the same carbon, water, and dust that Comet Swan now releases as it sails past the Sun. Every molecule that vaporizes from its surface is a thread in our shared story. Some of those molecules may even once have seeded life on Earth, only to return now as a new message. You were never alone in your origins. But Swan carries another message as well. A technological one. It reminds us of the fragility of our detection systems, the limits of our predictive models, the gaps in our cosmic awareness. In an age of artificial intelligence, quantum computing, and deep space probes, a comet still has the power to appear unannounced, silently approaching until it is already near. Are we being reminded of our vulnerability, or our resilience? Perhaps both. Comet Swan reminds us that our planet is not isolated within a void. It is part of a living, breathing system of celestial interactions. The sun sheds plasma, the planets tug on comets, comets shed material that becomes meteor showers, and Earth in its orbit continuously moves through the debris of the past. We are participants in a cosmic dialogue that began long before us, and will continue long after. So when we call Swan a cosmic messenger, we are acknowledging that its arrival is not meaningless. Whether one views it through the lens of science, spirituality, or philosophy, its presence brings insight. To scientists, it is a carrier of primordial matter. To historians, it is a link to ancient sky watchers. To dreamers, it is a reminder that the universe is still full of surprises. The messenger's message is simple, yet profound. Look up, pay attention. This universe still has more to say. And as Comet Swan glides across the heavens, it is not just light we are witnessing. It is communication from the oldest parts of creation, delivered on a tale of ice and starlight. As we look up into the cold October sky, we do not merely watch a comet. We witness a mirror held up to our civilization. Our defenses, our knowledge, our readiness, all reflected in a single arc of ice and dust rushing past our fragile world. There is a moment just before dawn breaks when the sky is at its darkest. Stars glimmer with ancient light, and the rising tail of Comet Swan appears like a distant torch, flickering at the threshold of night and day. In that moment, if one listens not with the ears but with the mind, a realization emerges. This is not just a celestial event. It is a crossroads. We stand at the edge of tomorrow, living in a time when our species holds telescopes in orbit, rovers on other planets, and the beginnings of permanent footholds on the moon. And yet a single comet, unannounced, unseen until it was already upon us, has reminded us that cosmic forces still exist far beyond our control. That even as we plan futures among the stars, we have not yet mastered the ability to fully detect what moves silently within our own solar neighborhood. Comet Swan is not a threat, but it is a test. A test of awareness, a test of humility, a test of readiness. Its sudden appearance from the solar blind spot highlights gaps in our planetary defense capabilities. Its unpredictable outbursts challenge our assumptions about cometary behavior. Its close approach, just 39 million kilometers, a hair's breadth in astronomical terms, reminds us that in the scale of the cosmos, safety is not an absolute state. It is a temporary condition. But within this uncertainty lies opportunity. For Swan is not only a mirror, it is a window. Through it, we see the early solar system reborn. We witness the materials that formed Earth, the compounds that may have seeded our oceans with life, the remnants of the great cosmic forge that made every element in our bodies. To witness this comet is to glimpse our past and our potential simultaneously. Standing on the edge of tomorrow means accepting that our future is tied not only to what we build on Earth, but to what approaches from the heavens. The skies are not silent, they are active, dynamic, alive with messages carved in ice and dust. The question now is not, what will Comet Swan do? The question is, what will we do in response to it? Will we continue to treat the cosmos as background scenery, beautiful, distant, irrelevant? Or will we recognize it as our true environment, vast, mysterious, and full of meaning not yet understood? We live at the dawn of a new era, an era in which comets are no longer just omens to be feared, but teachers to be studied. Swan's passing is not the end of a story, but the beginning of a deeper one. A story about our awakening as a species no longer confined to Earth, but connected to the entire solar system. And so, as the comet arcs across the sky and vanishes once more into the blackness, we are left not with closure, but with a calling. To look up, to learn more, to listen to what the universe is telling us. For tomorrow is not promised. It is discovered, one comet, one question, one awakening at a time. As Comet Swan drifts once more into the outer dark, its glow fading beyond the reach of our eyes, we are left not with fear, but with perspective. We have followed its journey from ancient origins to sudden awakening, from hidden approach to mysterious outbursts. We have seen how a single comet can remind us that our world is not isolated in stillness but immersed in a living, breathing universe. In its emerald light, we glimpse the ingredients of life itself. In its fragile structure, we saw the story of creation preserved for billions of years. In its unpredictable path, we were reminded that the cosmos is not a place of certainty but of wonder. Comet Swan asks us to reflect on our own place in this grand expanse. We are made of the same elements now streaming from the comet's core: carbon, water, dust forged in stars that died long before Earth was born. We are not separate from the universe. We are a continuation of it. A moment in its unfolding story. As you rest, remember this. Every heartbeat is connected to cosmic rhythms older than time. Every breath contains atoms that once drifted through space, perhaps even carried to Earth by comets like Swan. You are part of the same story of origins, of journeys, of transformation. So let your mind grow still. Let the vastness bring you peace, not fear. The universe is not against us, it is within us, around us, welcoming our curiosity. Tonight, Comet Swan continues its voyage into the unknown, and as it does, it leaves behind not just dust and memory, but a gift. The gift of awe, the gift of perspective, the reminder that even in the silence of space, we are never truly alone. Rest now, under the same stars that have watched Swan for millennia. The journey continues within you.